Hi everybody, Mr. Zarzak here, and in this video I'm going to talk about the cylindrical capacitor. So let's get to it. It's called the cylindrical capacitor because it's cylindrical. Okay, so we have two conducting cylinders, all right, that are separated by some gap. Okay, and the cylinder has some arbitrary length. So this area, let's do this. So this area in here, that's like the gap. Okay, and then you have this outer part, this outer cylinder here, and then you have this inner cylinder here. All right, notice that there's also this other little symbol over here, okay, which you might remember is a voltage source, okay, and in addition, if we zoom in, so the two terminals of this voltage source, this side's supposed to represent the positive, and then this is the negative. Okay, if I take and I trace out the wire, you can see that it jumps, so it's not connected to the outer cylinder. No, it's connected to the inner cylinder. Okay, so it's going to put this at a positive voltage, which means it's going to put a bunch of, okay, for what we're doing is we're putting about a positive charge distribution, okay, on here. All right, likewise, all right, the other side of this, oops, so if we trace the little negative wire, this is connected to that outer conducting cylinder like this. So everything along here, okay, is connected to the negative. So there's a negative charge density out here. Okay. All right, now if we knew the value of the voltage, great. All right, but that's kind of not the point. All right, we're supposed to be able to derive all this stuff. Okay, we connect electric field to voltage to capacitance. So we're going to start by deriving the electric field. Okay, the way we do that is Gauss's law. All right, so good old EDA is equal to the Q enclosed or inside over epsilon naught. Okay, so if I go back to my picture here, all right, so then it's in that space that's in between. That's what we're interested in here. So we have to imagine a little Gaussian surface. Okay, so this is look at this perfectly drawn cylinder. Okay, that's encapsulating this inner cylinder. That's my Gaussian surface. Now, what that really is that is a surface of uniform electric potential. I know it's not very pretty drawn, but you can imagine a little cylinder surrounding the inner cylinder, but not bigger than the outer cylinder. Okay, that's our Gaussian surface. It's a place of equal voltage. All right, so anyways, the next thing I have to decide is what kind of charge density am I looking at here? Do I want to use a volume charge density, a surface like an area charge density, or a line charge density? Okay, well, as long as I stay in between A and B, okay, well, then the electric field is just going to look like spokes. So like the electric field would go out like this from A to B. Okay, I'm going to erase that. I'm not going to keep that in there just so you can see it. But as long as I stay in there, it acts like I've got a line charge. See, so like these little blue lines, you can draw those anywhere you want. I'm like terrified to draw them anywhere else and have them not look awful. So you just have to imagine, okay, like the spokes, all right, of going from the center of a bike wheel out to the edges. Okay, so again, I'm going to use that linear charge density, which is just the Q inside of the little Gaussian surface over L. Okay, I could also write this as the total charge over the total length. Okay, and I can use combos, whatever I want. Okay, for this, I'm going to be using this here. So you'll see why here in just a second. If I take the lambda times the L, that's my Q enclosed, all right, for Gauss's law. So then if I sub that in, all right, E dA is equal to this lambda times L over epsilon naught. And when I evaluate the dA, which is just the tube part of the cylinder shape, remember no field would go through the end caps. All right, so then that's going to be the circumference, so 2 pi r times the length of this thing, so 2 pi rl is equal to lambda times L for epsilon naught. All right, so why did I do the little L? So I could cancel it. Okay, and so then I'm just going to take and rearrange this so that I can get my equation for the electric field. So all I got is lambda, okay, and then I have 2 pi. I'm going to group together all the constants, okay, and then r, that's my variable. So I have this like 1 over r function that describes the electric field as we go from the inside to the outside, okay, or from the inner conducting cylinder to the outer one. Great. So what? All right, once I have that, I can then work out the voltage between the inner cylinder and the outer cylinder. So delta V is equal to the negative integral of E dot dr. Okay, so then I have this function for the electric field that I worked out using Gauss's law. That's this, okay, times, or dot dr. All right, so then what are the limits of my integral? Okay, well, when I do my delta V, okay, so we want to go from the lower voltage to the higher voltage, which in general with these kind of things, we go from the outside to the inside. Okay, because out here, this is like the negative terminal that's connected to this part. Okay, so that's going to be that negative voltage out here. Okay, and this is going to be the positive voltage in here. Okay, so from the negative to the positive. So from B into A. Okay, so again, just general rule of thumb. If you have to guess, you go out to in. All right, so there we go. That's my setup. Delta V. Okay, pull out the lambda over your 2 pi epsilon naught B to A. And we get this 1 over R function dr. Okay, so that's we're integrating 1 over R. The rest of this is just constants and stuff. Okay, so then what the heck is the integral of 1 over R? All right, if you do not remember, we go to the AP equation sheet and it will tell us exactly what it is. It's that natural log function. It's ln. All right, so we're going to evaluate ln from B to A. Okay, so delta V is equal to negative lambda over 2 pi epsilon naught times ln of A minus ln of B. Okay, and since I have this negative out in front of the lambda, I'm going to distribute it because I just don't like it hanging out there. I find it more aesthetically pleasing. Okay, so ln of B minus ln of A. And I'm going to do one last step of simplification. Okay, this is an identity. If you have ln of one value minus ln of the other value, okay, you can write that as ln of the ratio of the two values, and this is equivalent to ln of B over ln of A, and 2 pi epsilon naught. So that little identity cleans up a lot of things, and it just gets used a lot in electricity and magnetism, so that's a good one to just kind of know. It's kind of like knowing that tangent of theta is sine over cosine. It just comes up enough to where it winds up being really useful to just remember that. Okay, anyways, so once I have this, all right, this is probably the right spot to make a little mental check here. All right, so we guessed that our voltage should go up as we go from the outside, so out at B, okay, into A. And we want to check this here and now, just because we're going to use this delta V to define the capacitance, or the total capacitance. All right, and that's got to be a positive value. So really what we need is this delta V to be a positive value. Okay, and it's really a matter of, is this positive or negative? Okay, and that's kind of the secret, all right, is that B is greater than A, all right, which means that this ratio here, so then like B over A is going to be some value that's greater than 1, okay? If I don't know what the ln function looks like, the natural log function looks like on a graph, well, then you should graph it. And so let's do exactly that. Okay, so I have this little ln of x already typed in. Okay, so if I graph it, it looks like this. All right, and what is this graph? Look, okay, when the graph crosses the x-axis, it crosses it at 1. So any ln of any number less than 1 is going to be a negative number. Okay, and then any ln of any number greater than 1 is going to be a positive number. So like ln of 1.00001 is a positive number. ln of 0.99999 is a negative number. Okay, so we've got B over A is greater than 1. This is going to be positive. So that's positive. Oops. And that's positive 2, which is exactly what we want. Okay, so now it's time for the capacitance. So let's take care of that. All right, so then capacitance is just our charge over our delta V. Okay, and here's where, let me bring this over. I wish I hadn't written all those little extra notes. Okay, so I got to erase some stuff. All right, go away. I guess I didn't really need to erase that, but oh well, too late now. Okay, so then we've got Q over this. All right, I'm going to clean up a little bit before, all right, I start dealing with that lambda and that Q, because that's really the next part is figure out how to get the Q and the lambda out of there. But first things first, I get 2 pi epsilon naught over, oh, don't forget that Q, over lambda times ln of B over A. Okay, so that capacitance is really, it's got to be defined just in terms of like physical parameters. All right. So that Q's got to get out of there. Lambda does too. So the way we're going to get rid of it is we go back to all this and say, lambda. Hey, look, lambda is also equal to the total charge over the total length. And the total length is that L. We got that part. And this has big Q in it, so we can use it to get rid of it. So 2 pi epsilon naught times Q over lambda, which is just big Q over L. Oh, come on back. No, too far. You pretend you didn't see that. You didn't see that. Times ln of B over A. All right, so we can get that Q out of there. Okay, a little bit more cleanup here. Let's get that L up on the top. So I have 2 pi epsilon naught times L over ln of B over A. All right, and if we look at the function once again, okay, this part here, all right, B is greater than A, so that little ln function is going to be a positive value. The stuff up on the top are all positive numbers. Our capacitance is a positive value, okay, which we need. Capacitance, how much can we hold? There's no negative capacitance, so we can put charge on these two cylindrical conductors or we can't. Okay, so now we've got our formula, which means we have reached the end of the video. We did it. Here it is. Thank you for watching. This is Mr. Zarzak saying I will see you next time.